Welcome to the next chapter. It is equilibrium and center of gravity. This is one of the shortest chapters in this video. Now, have you ever tried to balance an object, say a cupboard, with your fingertip? What did you observe? The object could only balance at one point. Now, this point where the object balanced is called the center of gravity. Again, if you have a uniform meter rule and place it on a pivot, it balances at the 50 centimeter mark, if indeed the meter rule is perfectly uniform. The rule is then said to be in a state of balance. All the clockwise moments equal to all the anti-clockwise moments, producing a net zero turning effect. The forces acting on this rule are the gravitational forces. The gravitational forces on the meter rule can be represented by a single downward force, which acts at the point of contact with the pivot due to the weight of the meter rule. Remember, weight is given by mass times acceleration due to gravity. W is equal to mg. Therefore, the center of gravity of a body is the point through which the resultant of the weight of all particles of the body acts. It is the point from which all the weight of the body appears to act. For regular objects, the center of gravity is at the geometric center. For irregular objects, it's located elsewhere. For an irregular shape like this one, we can determine the center of gravity using a plumb line. We make 3 holes near the edge of the object, which will allow it to swing freely when suspended from each of them. Next, we suspend the object from the point P as shown here. Hang a plumb line from the point P and mark on the plumb line P' on the object. Repeat the same with point Q and mark Q' so that we have line Q'. Follow the same procedure with hole R. Now you will observe that all the 3 lines intersect at one point, and this point is the center of gravity of this irregular object. Let's take an example. A uniform meter bar 100 centimeters long balances at the 20 centimeter mark when a mass of 1.5 kilograms is attached at one end. Now calculate the weight of the bar. You've also been given there that G is equal to 10 newtons per kilogram. Now in the solution, the term uniform means that the weight is evenly distributed along the bar, and it therefore acts through the center of gravity, that is 0.5 meters from either end. Since the system is in equilibrium and also taking the moments about O, weight is given by mass times G, which is 1.5 times 10, giving us 15 newtons. So clockwise moments equal to anti-clockwise moments. The clockwise moments are due to the weight of the bar. Anti-clockwise moments are due to the 15 newton weight. So we have 0.2 times 15, force times distance, is equal to 0.3 times W. 0.2 times 15 is equal to 0.3 times W. 0.3 is 30 centimeters, which is the distance from the pivot to the center of gravity. So if you divide both sides by 0.3, you will find W is equal to 10 newtons. 10 newtons is the weight of the bar. Let's have another example. Now, these two naughty boys are standing on a bar suspended by two ropes. One of the boys weighs 40 kilograms and the other weighs 50 kilograms. Now, assuming both are standing right at the point where the rope is tied to the bar, if the 40 kg guy stands 2 meters from the edge of the bar and the 50 kg one stands 1 meter from the other end, and that the bar is 6 meters long and uniform, weighing 2 kilograms. Now I want to calculate the tension on each rope. Calculate the tension on each rope. Did you give it a thought? Let's do it. Now you need to recognize the forces that are acting here to produce a state of equilibrium. Now the downward forces are the weight of the boys and the weight of the bar, which acts from the center of gravity. Vertical forces are the tensions on the ropes. So if I let F1 and F2 be the forces acting on the ropes, that is the tension. If I take the moment from side A, it means F1 is eliminated. Why? Because in that case it will be acting at the pivot and thus will produce no effect. Remember that? Again, if I take moment about B, F2 is eliminated for the same reason. Secondly, because the boys are standing right at the ropes, they produce no turning effect. They just add to the tension of the respective ropes. So if I remove the boys first and find the tensions due to the weight of the bar, the system is in equilibrium. So upward forces equal to downward forces. So F1 plus F2, those are the upward forces, should be equal to 20 Newton, downward force due to the weight of the bar. Remember, 2 kilograms is equal to 20 newtons. 2 times 10. Now taking moment about A, we have F2 times 3 meters, that is the distance, is equal to 20 newtons times 2. F2 times 3 is equal to 20 times 2. So I divide both sides by 3 and F2 is equal to 13.3 newtons. So we said F1 plus F2 should give us 20, and we have F2 as 13.3. It means F1 is 20 minus 13.3, which gives us 6.7 newtons. So without the boys, the tensions are 6.7 newtons and 13.3 newtons. So adding the boys, we shall have on the right hand side 13.3 newtons plus 400 newtons, that is 40 kilograms equal to 400 newtons, which gives us 413.3 newtons. On the left hand side, we shall have 6.7 newtons plus 500 newtons, which again gives us 506.7 newtons. Now think about this. Suppose the boys both stand at one of the ropes. What would be the tensions? Think about it. Now, whenever a body is at rest, all the forces acting upon it balance one another, and the body is said to be in equilibrium. The stability of an object depends on the position of its center of gravity and the turning effect of its weight about an axis or a point. Now, the factors that affect stability of objects include surface area of the base. Now, if the surface area is large, the line through the center of gravity of the body remains within the base, even if the object is tilted through a large angle. And therefore, a body with a broad base is more stable than one with a narrow base. Secondly, the position of the center of gravity. A body is more stable when its center of gravity is as low as possible. This can be achieved by making the base heavier. Bodies with high centers of gravity are less stable.
In the same year that Marie Curie received her second Nobel Prize, Ernest Rutherford did a series of experiments in which he bombarded a sheet of gold foil with positively charged particles. The positively charged particles he used were in fact part of the radioactive emissions of radioactive elements. What he found was that most of the particles passed through the foil undisturbed, suggesting that he was shooting them at mostly empty space and not in fact a solid sheet of gold atoms. Only a very small amount of the particles bounced back, suggesting that they came into contact with some immensely dense solid material. The conclusions that Rutherford drew from his research were revolutionary. It showed that atomic particles are made up mostly of empty space around a central core called a nucleus. And based on this work, Rutherford defined what we know today as the planetary model of the atom. In his long career, Rutherford laid the groundwork for scientists to understand the atomic structure. He discovered the proton, and he also showed that the nuclei of all radioactive elements undergo a spontaneous and random process of decay over time. It is this decay that caused the radiation studied by Becquerel and the Curies.